So in the earlier session, actually, we had seen time dilations, right? In this session, let's understand E equals to mc squared. That's what I told you. Well, this equation is known as, it's not E equals to mc squared. It is something called as energy mass equivalence. We call them energy mass equivalence equation. Okay, this is coming from straightforward from relativity theory, E equals to mc square. Well, this equation suggests that if you want to create some energy, if you want to generate some energy, then you need a mass of some way. This is your matter. Mass consists of matter, so we have a matter which is moving with a speed of light. Keep that in mind, that your c, that is speed of light, is in the form of square. Okay, so it is doubled. So speed of light is somehow related to, approximately it is 10 raised to 8 meter per second. So when you double it, it is going to be 9 into 10 raised to 16. So you need that kind of speed. So ultimately it is somehow not possible. But let's say we have this equation. So here this equation suggests that if you increase the mass, you're going to, you will get some high energy. If you decrease the mass, you will definitely get a decrement in the energy. So this equation is energy mass equivalence, which doesn't give you any time travel or something like that. This equation deals with energy and mass. So this equation basically deals with something called as conservation. I'm not going to deal with time travel or other things. I'm going to deal with this conservation of mass, or let me say it as energy, because both are equal term here. We can see this. They are relatively to each other. So conservation of mass and energy. Now the thing is, you have heard this definition that energy is not created, not destroyed. It can transform from one form to another form. So how it is basically, you all know that we have three states of matter, which is solid, then we have a liquid, and then we have a gas. Actually, it's not three. We have another one that is known as plasma, but this is not a discussion point right now. We deal with this solid, liquid, and gas. So let's understand this, that relativity theory suggests that mass cannot be created, not destroyed. It transforms from another form to another form. In a very similar way, as it is equal, that energy cannot be created, not destroyed. It transforms from one form to another form. So the thing is, if we have a mass in the form of water, right, and when you convert this state, right now water is in the form of liquid. So when you convert this liquid state into a solid state, then water gets going to be in the form of ice. So this ice. So when you weigh this water mass, let's say it is in the m1, it is the weight of water in the form of liquid. And when you convert this transformation, when you do this transformation, it is in the ice form. Again, if you weigh, the mass is going to be the same, m1, m1. This is not equivalent to only two transformation. If you go for third one, water to gas, when you heat this ice, again you will get if you somehow, let's say, if you get it's definitely, it is not, I have to convert it again like this, water to, if you go for if you heat it up, it's going to be gas, right? So again, if you weigh it, you will get the same mass. So mass is not, you cannot create it, again you are not destroying it, you are just transforming from one form to another form. And that's the idea of E equals to mc square. And that's why we have hydrogen bomb, atomic bomb, and other equivalent theories. So this equation suggests that conservation of mass and energy, right? So if you want to generate some energy, you need a mass. Keep that in mind, that this mass is a rest mass. It is stationary. It is rest. It is resting. It is not moving anywhere. So this is a rest mass, and which is moving with a speed of light. Okay, so mass is resting, but it is moving with a speed of light. Then you can generate energy, okay, which is equivalent to this mass. So this is your conservation of mass and energy. Now relativity theory suggests something else other than this E equals to mc square. It is not, it is just a part of relativity theory. Another part, it says that when you move this mass, ultimately this one, when you move this mass with some speed, this mass is going to be heavier. It gets incremented, plus m plus m plus m. It's going to be heavier and heavier and heavier when you increase the speed, when you increase some velocity or speed, when you increase that, mass is going to be heavier and heavier and heavier. That's the idea of relativity theory. That is the another part. This is the first part, this is the another part. So this equation actually, it is something like this: E equals to mc square plus some kinetic energy. It needs that. So this is your kinetic energy. This equation is only for stationary objects, but everything is not stationary, right? Something is something relative. Something like, as I told you in the previous thing, that we are relative to Earth and Earth is related to universe. So ultimately all are related to each other. So in a very similar way, this equation is related to something else. So that is kinetic energy. So we have E equals to mc square plus k. So if you see, if I theorize this, as I theorize this, that as I told you, that if you increase the velocity here, your mass is going to be increased, okay, it's going to be heavier. But if you see this equation, what it is actually, you know, contradicted. See, E equals to mc square, but when you rearrange this form, you will, what do you get? You will get E by c square equals to m. And if you see the rearrangement, if you increase the speed of light here, your mass is going to be decreased. So this is completely contradicted, right? If you increase the speed, your mass is going to be, you know, lowering, it is lowering down. So this equation is not suggesting you that, it is not, you know, giving you the relevancy here, that if I increase the speed, your mass is going to be heavier, but it is not giving you here. So this equation is not giving you, okay, that thing, because it is stationary, okay. If you want to see that where exactly my mass is going to be increased when I increase the speed, if you want to see, then we have another equation, and that equation is this. It is coming from here, this from kinetic energy. That's why, as I told you, it's the one, it is the first part and this is the second part, and I'm showing you the second part. So we have a mass who is moving, okay, so this is a moving mass, and this is the mass which is stationary, coming from here. It's a stationary mass. Then I have a 1 minus v square divided by c square, and it's going to be under root of that. And that's the equation of, you know, moving mass. Now if you see if you put some values here, you will see whenever you increase the velocity, definitely you will increase the mass, and I mean it's going to be heavier and heavier. If you want to see this thing, see, I have this. So the thing is, I have a mass, okay, this is stationary mass, this is rest, okay, it is resting. So it is 10 kg. Ultimately in the initial you know, thing, I have a mass of velocity of 50. It's double 2500, and then I have a c, that is 3 into 10 raised to 8, which is to be 9 into 10 raised to 16. You are getting the same mass. Change the values of v. Right now it is 1000. You are having 10 kg again. If you equate in this equation, put those values in this equation, and you will get it, okay, you will get this m here. Then 10 kg again in m naught, and then I'm increasing somehow 2 into 10 raised to 3 my velocity, and I'm squaring it. When I equate for my m, I'm again getting the 10 kg. But when I change the value here, 2 into 10 raised to 4, and I again square it, you will see there is an increment. You see 10 0.00002 kg. It is 10 ultimately. I should get the exact 10, but right now I'm getting, you know, heavier object here, heavier mass here. Again I increase the velocity, again I'm getting the increment. Again I increase the velocity, again I'm getting the huge increment, 13.4164. And if you go by this and so on to something called as v equals to c, that means velocity equals to speed of light, and you are squaring it both these terms, 3 cross 10, 3 cross 10, and you equate this, what do you get? What you will get? Again you will get something called as 10 divided by 0. Ultimately 1 divided by 0 is infinity, right? So you're getting infinite mass over here. So that's the thing. This equation, basically this equation give you that whenever you increase the velocity, your mass is going to be heavier and heavier and heavier. It depends on your values, basically. So this equation suggests you. But if you see the keen observation here, on a very lower speeds, these speeds are lower, okay, and these speeds are something like our day-to-day speeds, car, rocket, and rocket science, or space shuttles speeds. These are somehow the normal speeds, and you are getting the same mass. You're not having any increment. When you will get the increment, when you have a very higher speeds, the speeds such as black hole speed, as wormholes, or the gravitational pull, when there you can see this increment of mass. So this is the perspective of observer to observer, okay. You will not see this increment if you are at stationary, You will see only this increment of mass when you are moving with a speed of some velocities, and it also depends on the observer to observer. Okay, so this is this equation, the two equation we had seen, that's the E equals to mc square for stationary objects. And if you want to see, and if you want to see the another perspective of equation, that is the kinetic energy. In this one, this is the kinetic energy of part. So cumulatively you will get this E equals to mc square plus k, and that's this one for moving objects. Now another idea over here, we have something called as Large Hadron Collider, right? And which also gives you that relevancy equals to mc square. Now what exactly it's doing is having a huge underground tunnel, some miles, and we call them 16 or 19 miles, and we have a proton inside that which is moving with the speed of light. Now as I told you, whenever we move with the speed of light, its mass should increase. It's getting heavier and heavier, but it is not getting here. So maybe it is getting, but I don't know about that, but it should be heavier and heavier whenever you increase the speed. That's the first part of Large Hadron Collider. Second part, they are finding the genesis, and before the genesis what happens. So ultimately they are finding one last stack of particle or subatomic particle, which is from the boson. So they are finding Higgs boson, which is a particle of genesis. It means the generation of universe. That's the relativity theory doing it. So I hope you understand somehow the things which is a part of relativity, and also this you understand that normally you will not see any increment. Your day-to-day routine life will not give you any increment in the mass, but somehow if you observe, whenever you walk very very fast, your legs going to be pain, and you will get some friction, you will get some pull by your legs, that my legs are heavy, and that heavier thing is nothing but this increment of mass, because you are moving with a fast speed. At a normal speed you will not get any pain, but if you go faster, a little bit faster, your legs going to be pain, right? And that is why it's the mass increment, and that is somehow related to E equals to mc square. I hope you understand it, and we'll see another things somehow related to relative theory in our next session. Thank you so much for listening to me.